Imagine if your favorite language model could think deeper, not just by churning out answers, but by evolving its responses like a digital Darwinian experiment. That's exactly what mind evolution does. Using a genetic algorithm, this approach generates, recombines, and refines solutions, all while avoiding the need for formal problem-solving frameworks. Think of it as a brainstorming session on steroids, where the LLM plays both the critic and the author, iteratively improving its ideas. From travel planning to stenographic poetry, yes, you heard that right, mind evolution outperforms traditional methods, proving that sometimes the best way to solve a problem is to let the model evolve its way to success.
Let's begin by looking at an idea called mind evolution. It's all about helping large language models, LLMs, think more deeply, especially when facing tricky tasks. Imagine you're trying to solve a really complex puzzle. You can't just rely on one shot of reasoning. You need multiple attempts, feedback, and a way to refine your thoughts. That's where strategies like chain of thought, self-consistency, and iterative revisions come in. Mind evolution takes this further, with a genetic approach inspired by evolution in biology. It creates a bunch of different candidate solutions, uses feedback from an evaluator to improve them, and blends both creative, divergent, and selective, convergent thinking. Instead of evaluating each step in a solution one by one, it refines solutions as a whole. And it can even run multiple refinements in parallel. It also handles problems that are tough to formalize. All you need is a good solution evaluator. The paper tests this strategy on tasks like travel planner and natural plan, which require coming up with solutions only described in natural language. For example, travel planner has constraints on accommodation, dining, and budget. Typical LLM strategies often fail there, but mind evolution reportedly solves over 98% of these tasks, even without formal solvers. This sets the stage for how evolutionary methods can make LLMs more powerful at inference time, especially when handling real-world problems that aren't easy to encode with strict formal rules. Ready to see how this works in practice? Here, we dive deeper into how mind evolution performs on natural language tasks, focusing on travel planning. Take a look at any example you see in the paper. They've provided a visual to demonstrate. The system starts with a bunch of sample travel plans and checks them against certain constraints. Maybe there's a strict budget or specific dining preferences. The system then refines these solutions based on the feedback it gets, much like evolution in nature. The results are quite notable. While something like a best event approach might only reach moderate success, mind evolution jumps to a 95.6% success rate on travel planner and 85.0% on meeting planning. And that's with no fine-tuning. When they add a second refinement stage with a more powerful LLM, Gemini 1.5 Pro, they get close to perfect 100% for travel planner and 98.4% on meeting planning. They also introduce a new benchmark called Steg Poet, where you hide secret messages in poems or essays. Mind evolution hits 87% success there, showing it's not just about travel itineraries. Its direct optimization in natural language is the key. Unlike older methods that need formal problem translations, this approach works purely with text. Think of the possibilities this opens up for real-world use. Now let's look at the core methodology. Mind evolution uses genetic algorithms which mimic natural selection. You might recall how evolution works. Individuals in a population with higher fitness are more likely to pass their genes on to the next generation. Here, each individual is a candidate solution. The better it solves the problem, the higher its fitness. The system then selects parents, does crossover and mutation, and generates new solutions. They also use an island model. It keeps separate groups of solutions evolving independently, but sometimes the best solutions migrate between islands. This prevents everyone from getting stuck in the same local optimum. Another trick is periodically resetting weak islands and replacing them with stronger solutions. What's special is that all of this happens using language prompts. Solutions are written in natural language, and the LLM itself performs crossover and mutation by editing text, so it's harnessing the model's natural skill at generating and understanding language. Ultimately, the process runs until a valid solution appears, or until they hit a generation limit. Intrigued? Let's keep going. Here, they introduce important components that make mind evolution tick. Check out Table 1, which outlines hyperparameters like the number of solutions in each population, the frequency of island resets, and even the probability that certain conversations among solutions won't have a parent. All these knobs control how diverse the solution population remains, and how aggressively it searches for an optimal plan. Now look at Figure 2, where they illustrate refinement through critical conversation, RCC. In this setup, the LLM acts both as a critic and an author. First, the critic finds flaws or inconsistencies. Then, the author adjusts the solution based on that feedback. If a plan forgot that you need 5 days in Tokyo instead of 3, the critic points that out, and the author fixes it. This process repeats until all constraints are met. They also stress that textual feedback is crucial. Checking whether a plan meets the constraints might be easier than producing it from scratch, but it still boosts performance significantly. Initialization comes from prompting the LLM with a problem description. It generates first-pass solutions, and then RCC keeps improving those. It's a straightforward but effective loop. Now let's explore the evolutionary mechanics in more detail, along with the experiments. Mind evolution selects parent solutions mostly based on fitness. But sometimes less fit solutions get chosen too, just to keep the gene pool diverse. Crossover and mutation happen in one shot, guided by that same critical conversation process. After each generation, newly refined solutions join the population, and duplicates are tossed out. They also do migrations between islands. Top performers circulate among them, speeding up progress by sharing good genes. Resets happen at set intervals, where underperforming islands get replaced with globally strong solutions. Sometimes the system picks those winners by raw fitness. Other times, it uses an LLM-based selection to ensure variety. For experiments, they tested mind evolution on trip planning, meeting planning, and travel planner benchmarks, all in plain text. They used the Gemini 1.5 Flash model by default, but for tougher problems, they added a second stage with Gemini 1.5 Pro. Baselines included simpler methods like single-pass generation or multi-turn refinement. The goal was to see if mind evolution could outperform these more straightforward approaches. To measure success, they track how often each method actually solves the problem, success rate, and how much it costs in terms of LLM calls, tokens, and other resources. That helps everyone see the trade-off between performance and expense. Check out the results in the travel planner task. Users want detailed trip plans under certain budgets and preferences. Mind evolution hits over 95% success, way ahead of best of or sequential strategies that manage around 55.6% to 83%. With the two-stage approach and Gemini 1.5 Pro, it basically hits 100% on validation and 99.9% on test data. Again, no formal solver needed. Look at Figure 3 to see how success rates vary by problem difficulty and trip length. One-pass methods drop off fast as complexity increases, but mind evolution stays strong, thanks to its iterative approach. They also tested something called the natural plan trip planning task, involving city connectivity and scheduling. Here, mind evolution scores 96.2% and 94.1% on validation and test data, beating the baselines by a large margin. The harder the task, the more mind evolution's iterative strategy shines. Next, they show a broader performance overview across several benchmarks. Take a look at Table 2. It compares success rates and costs on travel planner, trip planning, and meeting planning. Mind evolution, especially with its two-stage approach using Gemini 1.5 Pro, almost aces everything, over 99% on test data for travel planner, for instance. That's a big gap compared to simpler strategies like Best of N or Sequential Revision Plus. Figure 4 zooms in on how performance changes when the trip planning scenario includes more cities. Baselines like One Pass and Best of N start struggling, but mind evolution holds up. Meeting planning is particularly tough because not every scenario can be perfectly scheduled, yet mind evolution still hits an 85% success rate on validation and 83.8% on test data. After the second refinement stage, it climbs to 98.4% and 98.2%, showing how effective the evolutionary approach is for these constraint-heavy problems. Here, you'll see more examples and analysis. Glance at Table 3, where there's a trip planning problem with strict requirements like visiting specific events. Mind evolution meets all the requirements, whereas Sequential Revisions Plus forgets an annual show in Madrid and uses a flight that doesn't exist. Best of N messes up the city durations. Figure 5 shifts focus to meeting planning. The bigger the group, the harder it is to sync everyone's schedule. Yet mind evolution stays strong. It performs better than Best of N and Sequential Revisions Plus in nearly all tested conditions. They also look at scaling and ablation. Figures 7 to 9, if you peek ahead, show success rates go up when you allow more candidate solutions or more generations. Baselines don't adapt as well because they don't use the same feedback loop. Mind evolution, by contrast, learns from each round of feedback. This is where its ability to learn common sense constraints becomes valuable. Continuing with analysis, Figure 6 illustrates how success rates climb across generations for each task. Mind evolution leads all the way. Figures 7 and 8 show that upping the number of candidate solutions pushes success rates even higher, especially for travel planner and trip planning. Compare this to sequential revision plus or best of n, which don't improve as much from extra generations or extra solutions. Figure 9 looks at meeting planning, which grows more complex with each new scheduling constraint. Mind evolution still maintains an edge, likely because it refines solutions based on textual feedback and an evaluation function that's suited to real-world rules. Table 4 shows what happens if we remove certain features. Skipping the critic step or textual feedback really hurts performance. Island resets guided by the LLM also help, though not as dramatically. Then, Table 5 explores different hyperparameter setups in the trip planning task. The island model stands out as a big reason mind evolution does so well. It keeps generating fresh solutions without getting stuck. They also discuss balancing the number of candidates per generation with the total generations, which helps fine-tune the cost-to-performance ratio. Now let's talk about a creative test called Steg Poet. It's a neat challenge. You have to hide a numeric message within a poem or essay using a substitution cipher. Look at Figure 10 for an example. You can't just list all the numbers. You have to weave them into the text at certain intervals so the average spacing meets a set constraint. Check out Table 6, where different methods are compared on StegPoet. Mind evolution hits a 46.5% success rate on validation right away, beating out sequential revision plus and best of n. When they add the second stage, plus pro, it jumps to 87.1%. Figure 11 gives a visual look at how success rates change with difficulty. As the spacing constraint gets tighter or the message gets longer, everything becomes more challenging. Still, mind evolution adapts better than the baselines. This demonstrates that mind evolution isn't just for scheduling or itinerary tasks. It can also handle creative tasks that blend constraints with artistic output. Finally, we arrive at the conclusion. The key takeaway is that mind evolution offers an evolutionary search strategy tailored to natural language planning. It uses a mix of broad exploration and iterative refinement, and it surpasses simpler methods like best of n and sequential approaches. It also hits impressive success rates on benchmarks like Travel Planner and Natural Plan, all without specialized formal solvers. They do note some limitations. The approach currently needs tasks that can be programmatically evaluated and critiqued. Future work might expand to more generalized evaluators built into LLMs, opening the door to even broader scenarios. The acknowledgements give credit to everyone who contributed to the project. In essence, this study shows how evolutionary thinking can amplify the problem-solving power of LLMs, making them more versatile and effective on complex, real-world tasks. Thanks for diving into this with me. It's been a fun journey through the world of mind evolution.